So this video is an introduction to what we call the fundamental theorem of algebra. And as a little warm-up, take a second and look at these graphs, pause the video and see how many roots do you think these functions have. Remember, roots is the same thing as just the x-intercepts of the graph, also called the solutions sometimes, or the zeros, because it's where it hits zero. So, how many roots do these functions have? This first line only has one root, right here, where it hits the x-axis. This one right here has two roots, one there and one there. This one right here has three roots, or three solutions, or three x-intercepts, or three zeros, here, here, and here. All right, so hopefully that was a good little refresher. Think about the equations for this. Like, the equation for this one would be a line, something like x plus 1, and you're trying to see where it equals 0. And the equation for this would be a quadratic, something like x squared plus or minus something. And this one right here is a cubic, so it would be like x cubed with some other numbers in there. Do you notice a pattern between these equations and the number of roots that they have? So the pattern is the highest exponent tells you exactly how many roots it's going to have. Notice that this one has an exponent of 1 and it has one root. This one had squared, a 2, and it had 2 roots. This one was a 3 and it had 3 roots. That is the fundamental theorem of algebra. A polynomial of degree n will have exactly n roots. Let's break this down a little bit. First of all, what does degree mean again? Degree, if you remember, is the highest exponent, so the biggest exponent in your polynomial. So this, in more simple terms, is basically the highest exponent in your polynomial, the degree, tells you how many roots or solutions or x-intercepts it has. Here's a little disclaimer though, and this is a little misleading. They could be complex roots, which, remember, complex numbers involve imaginary numbers, something like 2 plus 3i. That's a complex number. So they could be complex roots and not actually hit the x-axis. But it's still a cool theorem that the degree literally tells us how many solutions we're looking for. You may have noticed, like, when we were doing linear stuff, something like this, when you solve it, obviously only has one solution. And then you may have noticed the entire quadratic unit, we always had 2 solutions, or usually. That's because it has a degree of 2. All right. So here's a few examples. Let's think about a quadratic. And a quadratic has to do with x squared. It may have some other numbers in there. When we graph a quadratic, typically it has 2 roots, like this one and this one, or if it were upside down, there's a root and there's a root. But there are other ways to have quadratics. For example, what if it doesn't hit the x-axis? What if we have a quadratic like this? That one has no real solutions because it doesn't hit the x-axis. But we know, since it's a quadratic, and that's x squared, that it's going to have 2 solutions. So where are they if there are no x-intercepts? We know then that these must be complex solutions. They must be 2 imaginary solutions that have to do with I, the imaginary unit. It's also possible to have one other option, which is, what if you hit right on the x-axis and then go back up like this with the vertex on the x-axis? In that case, you still have 2 roots. It's just that the root is the same. You have a solution of -5 and another one of -5. And so you had They were just the same, and so that's why you only hit the x-axis that once. That's called multiplicity, by the way, if you ever hear that. This is called, there's a root of -5 with a multiplicity of 2 because it's there twice. Is it possible with a quadratic to ever have, so far we had 2 real roots, we had 2 complex roots, and even in this weird scenario, this is still 2 real roots. They would just happen to be the same. So do you think it's ever possible with a quadratic to get 1 real root and 1 complex? Hopefully you thought about that for a second. The answer is no. With just a parabola, you either have to hit it twice, or not at all, or a situation like this, which is still 2 real roots. Let's think about a cubic function. So x cubed plus some other numbers in there maybe, but this would be a degree of 3, so we know that there are 3 roots. Let's think about some of these scenarios and what they might look like. So if I had something like this, that would be 1, 2, 3 roots. It could also be coming down in a negative direction, something like 1, 2, 3. So that would be 1, 2, 3 roots. But there are other options. For example, what if I had something like this? This would still be a cubic graph, but it only hits the x-axis the 1 time. So this would be 1 real root, and I know there are 3. It's just like I kind of missed the x-axis right here, and I missed the x-axis right here. So I know that this little hump here basically gives me 2 imaginary or 2 complex roots. That could happen the other way as well, like something like this. That would also have 2 complex and 1 real root. Is it possible to have all complex roots with a cubic? The answer is no. With a cubic, if you start up here, you have to end down in the bottom right eventually. Like even if I try to avoid it, like I can't, I have to keep going down and cross the x-axis eventually. Same thing if I were trying to go up and avoid the x-axis, I have to go up eventually to make it 1, 2, 3, a cubic function. So it's not possible to have all complex roots with a cubic function. Typically what you'll notice is that complex roots happen in pairs, something like these 2 right here. Okay, and then we can get really crazy stuff, like if you had like x to the 7th or something like that, there would be 7 roots. Again, some of them might repeat and some of them might be imaginary, but it's possible to have a graph that crosses the x-axis 1, 2, 3, 4, 5, 6, 7 times and looks like this. See how there's 1, 2, 3, 4, 5, 6, 7 roots. And again, sometimes it doesn't look quite so nice, but okay. So again, the degree gives you the number of roots. So pause the video and try each of these. How many roots do each of these have? All right, hopefully you've tried those. On the first one, since the highest exponent is a 2, 2 roots. This one, if we were to multiply this out, the highest exponent would be a x squared. And so again, 2 roots. That makes sense. Those are quadratics, so we know they have 2 solutions. Same thing here, 2 roots. The highest exponent on this one is a 1, so it only has 1 root, which makes sense. That's a line, so it's only going to cross the x-axis once. This one is a cubic. That's its highest exponent. It's degree 3, so this one has 3 roots. And lastly, the biggest exponent here is a 5. This is degree 5, so it has 5 roots. I wanted to real quick go through a few of these and show you. We'll review this later on, but if you were to factor these, you could actually find the roots. Like what multiplies to give you 8 and adds to give you 6 would be 2 and 4. And then you could set those two factors equal to 0 and solve, and this would be -2 and -4. Those are your two roots that you were looking for, right here at -2 and -4, and it would look like this. Or like on this one, if we wanted to see where it equals 0, we could just solve for x by subtracting 1. So -1 equals, and then to get rid of the squared, we'll square root. Notice this is going to be imaginary because I just square rooted a negative, which is I, and then add 3. Oh, and plus or minus because of the square root. So my solutions on that one were plus or minus I plus 3. Again, that's two solutions. They're just imaginary. Positive I plus 3 and negative I plus 3. This one, number 3, if you were to factor this, what multiplies to give you 9 and adds to give you -6, that would be -3 and -3. And you'll notice if we set those equal to 0 and solve, we get 3 and 3. That's one of those where you have multiplicity, where the roots ended up being the same. So you have a root of 3 and another root of 3. And so it would hit right here at 3, and it would look like this. Again, these are two real roots, because they're still real numbers. Or if you wanted to solve this one, see where it equals 0, you would just subtract 1, and then divide by 3. So -1/3 is the root for that line. Again, it only has 1 because it's a degree of 1. Anyway, just wanted to show you, connect to some of the stuff we did last year in Algebra 1. All right, go ahead and on your own, this is your practice, try these 4, just say how many roots it has, and then I would recommend graphing them in your calculator or Desmos and see what they look like. And I'll show you, I put them into Desmos as well. So this first one has degree 4, so it should have 4 roots. And you'll notice it has one real root here and one real root here, but somewhere in here we must have 2 complex roots. This one has a degree of 5. You'll notice it hits the x-axis 1, 2, 3 times, so it has 3 real roots, meaning 2 are left over to be complex. Probably that happened here. This one is a quadratic, and you can see it's 2 roots here and here. This last one has degree of 7, and so we would expect 7 roots. Notice I only see 3 x-intercepts, so it's possible there are some other complex roots. It's also possible that there's some multiplicity, that maybe some of those roots repeated, probably here around 0. I would guess that 0 is a root